try to do a review for our upcoming exam. I can't do everything because there's a lot of material, but I'm going to try to pick out a few things that people usually have a lot of trouble with. Again, I put out some YouTubes. You should watch those YouTubes. It's really important that you have good notes, and if you don't have good notes, try to get some notes from someone else, because some people are not taking good notes, and that's a problem. Also, it's really important to come to class. Some people don't come to class. If you don't come to class, you're not going to have notes. If you don't have notes, you're not going to have good notes. I mean, that's just a fact, okay? And again, if you're struggling, move up to the front of the room. Don't sit in the back of the room. I find there's a direct correlation between missing class and not doing well in the course. That's not always true, but that's usually true. Okay, so anyway, the first thing I want to review is oxidation, okay? People didn't really know why I put the quinones in, where I put the quinones, but it's because it was a type of oxidation. Generally speaking, oxidations are eliminations. Not all the time, but frequently, okay? So a typical elimination would be you put some leaving group on the oxygen. That's what's peculiar about them. And some kind of base pulls this hydrogen off. These electrons come in. This comes off. And you end up with a carbonyl of some kind. That's an oxidation, okay? The reverse, right, is a reduction. A reduction, this is just making sure you understand this properly. A reduction, you might have the carbonyl, right? And then you would add a hydride of some kind. The hydride could come from LAH, sodium borohydride. It comes in here, this opens up, and then eventually, not immediately, this is protonated somehow. Okay, this is very general what I'm writing here. Okay, similarly, Grignards and organolithiums are reductions because they break that pi bond. Okay, all right. So, but most oxidations are eliminations. Okay, so let's focus on that a little bit. All right, now, that being the case, there's two different scenarios that you have to deal with, okay? One scenario is when there's water present. Okay, when there's water present, the reagents are H2, CrO4, KMNO4, K2, Cr2, O7, in sulfuric acid. That's potassium dichromate, or sodium dichromate it could be. And then I've mentioned you could also use bleach with acetic acid, as we did in the lab. These are all aqueous conditions. Aqueous conditions. That means there's water present. Is there a problem?
No.
Okay. Then there are anhydrous conditions, right? Anhydrous conditions are when you have chromium trioxide impurity. Okay? Or PCC, as people like to say. But frankly, I would rather have you write a reagent down than an acronym, because I feel when people say acronyms or write acronyms, they don't really know what they're dealing with. Okay. The only mechanism I'm holding you responsible for is that one. Okay? So, but as I said on the sheet, I want you to be able to outline oxidation. Okay? So, notice this. Chromium trioxide. Chromium trioxide. You would draw this structure. Clearly, if you have H2CrO4, which has this structure, this is the hydrated version of chromium trioxide. Think about that. Like, just think about that structurally. Sulfur trioxide, right, is the anhydrous form of sulfuric acid. Okay? All right, so that's kind of like the basic stuff. These are going to be more potent than this is in general. Okay? So let's talk about what happens in an oxidation. So one of my primary goals in going over oxidation with you was to make sure that you understood how you make carboxylic acids. And I gave you a whole list of ways to make carboxylic acids, but there were only a couple that I went over. One method, right, that's very important, and you really need to know, is you really need to know how to convert a primary alcohol to a carboxylic acid. okay? One way to do this is to add chromic acid to it, okay? This will make a carboxylic acid. And what it says on that list I gave you is you have to be able to outline this process. What I told you in class is you always make some sort of an ester or some kind of a leaving group. With chromium, it's a chromate ester. With manganese, it would be a manganate ester, okay? So if I had this, and I were outlining what's happening, and I wrote out the structure like this. And I feel like people didn't get this the first time around, and I know you did not do this the first semester. Like, it became increasingly apparent to me that you just memorized these. What you memorized was the idea that of oxidation, and that if you should know this, if you have more hydrogens, these are the beta hydrogens in the reaction. If you have more of these, there's going to be a greater propensity to oxidation or a greater oxidative potential. Okay, you get more oxidative steps. So typically what these reactions involve is you make a chromate ester. I don't expect you to write this mechanism. I've said this many times. But essentially what it consists of is the oxygen hitting the chromium's super positive, and you're losing a water molecule. That's what's happening. And you could write something reasonable for that, but I just generally don't see mechanisms written for that. Okay, then what happens, as I've discussed, is that this chromium is extremely positive. It's in a +6 oxidation state. What that means is it's pulling electrons. It's pulling electrons toward the chromium, okay? This is very odd because oxygen normally is negative, delta minus. This is sort of a delta plus oxygen. And when it's really losing its density, this is not like hydronium ion. Hydronium ion, okay? Hydronium ion, this is a bookkeeping charge, and the oxygen still has its lone pair, and it still has all 8 of its electrons. This is actually losing its electron density. So it's desperate. So what does it do? It pulls the electrons in, and then, something, probably water, pulls that H off. But the point I'm trying to make here is that in elimination reactions, it's not all about the base. Everybody gets obsessed with the base. It becomes a little more about the leaving group. And when the leaving group is extraordinary, you can have a really good leaving group and a really weak base, and the reactions will still work. So what I call this is an electron sink. The electrons are sinking in toward that chromium. The oxygen is so positive that it's taking the beta hydrogen electrons and then just dumping the proton off into the solution. So I say it just kind of comes off incidentally. A lot of students haven't grasped that yet. Sit down and study it, okay? What you get out of this is an aldehyde, and the chromium is actually in a +5 oxidation state, but it will cascade down. It will cascade down into chromium 3, which is this green solution, okay? So here's the problem. If you're in water, one of the things we know is that when you're in water, you get hydrate. Hydrate is not a big problem in most cases, but this is a place where hydrates really come into play. And as you learned before the last exam, most of it's in the ketone, the carbonyl form, because the carbonyl is very stable. However, you get this tiny bit of hydrate. Where's the water coming from? The reagent has water in it. So any of those reagents I listed that have water in them can do this, okay? So then what will happen? Well, what will happen is you'll make more, because remember, reactions don't occur in lockstep. It's not like 8 million molecules all react at the same time and there's no chromic acid left. There's still chromic acid left. So you have to think of it that way, that there's a lot of stuff going on in here. It'll make another chromate ester. Okay? But the problem with an aldehyde or a primary alcohol, what was a primary alcohol, is that it still has a beta hydrogen. So what will happen is the same reaction. This will come off, this will come in, a water will pick this up. You should understand this. This is an important concept in oxidation. But it is a way to make carboxylic acids. So it's very hard to stop those. Okay? So what you learn in class is you say, oh, we can stop them. We can stop these reactions. Okay? I'm sorry, because again, my thing I usually support this with is broken. All right, so you say, well, how do you stop it? You stop it by not having any water around. If you don't have water around, it won't happen. And also, if you don't have any more beta hydrogens, it won't happen. So for example, if you take this, right, this is a secondary alcohol, and you add chromic acid to it, all right, and it makes a ketone, and you say, oh, these are hydrous conditions. These are not anhydrous conditions. I'm going to get some hydrate. It's true, you're going to get some hydrate. But look at this. There's no beta hydrogens. If there's no beta hydrogens, it can't eliminate. So it doesn't. It just stops. It just backs up and it stays as a ketone. So you're good on that one. Okay? How else can you stop it? Remember, tertiary alcohols won't react at all, right? Tertiary alcohols don't react at all because they don't have beta hydrogens. I always tell people to get an elimination reaction like this, you must have a beta hydrogen, and they're here. This is the alpha position, this is the beta position, and the leaving group has to go there. You have to have a leaving group and a beta hydrogen to essentially get these reactions to go. What's peculiar about them is you put the leaving group on the oxygen, and you don't break the bond here, you break the bond over there. And that's what bothers people, okay? The other way to stop it, so a tertiary won't react at all because it has no beta hydrogen. All right, so how else can you stop it? Well, you can stop a primary at the aldehyde, and a lot of people have this memorized, and they just have this one reagent just like blazoned into their head, which is the PCC reagent. But I want you to know why that happens, okay? So if you have a primary alcohol, and again, the beauty of most of this chemistry is that it's pretty straightforward once you get the patterns down. But I wrote this mechanism in class. This is the mechanism I expect you to know how to do. So this, okay, will attack and we wrote this several times in class, so this should be in your notes. The problem is, do you have good notes? That's the question. So then you'd have a proton exchange. Now this is just, as I said, kind of an approximate mechanism. But remember, this one is done, when you use chromium trioxide, it's dehydrated, and this reaction is done in pyridine as your proton scavenger, okay? So you can view the pyridine as the molecule that's moving the protons around. Now, it's going to eliminate the same way. So this is delta plus. This is a chromate ester. Again, you're always making this thing. Whether you're in water or not with chromium, you're making a chromate ester. This bond is really polarized. That's your electron sink. This pulls this proton, these come in, and that comes off. That gives you the aldehyde. Now, what's the difference here? The problem, of course, is that you have a beta hydrogen left. But the difference is you're under anhydrous conditions, so you can't make a hydrate. So I'll reiterate, it's kind of a good concept to know. It's a great way to make carboxylic acids, okay? You can make them for primary alcohols, but just realize that the way it happens is that it first becomes an aldehyde, the aldehyde hydrates, and then the hydrated product still has a beta hydrogen because it was primary, and so it can form another chromate ester and eliminate, and when it does, it makes a carboxylic acid. A lot of times people are not aware of how that happens, and it's important. And we have to know how to make carboxylic acids because carboxylic acids can be converted into derivatives, okay? All right, now, before I get off the oxidation topic, okay, just remember you have to know, you have to know mechanisms for oxidation of dihydrobenzoquinones. Okay, I'm going over this because this is just something a lot of people ask me about. All right, so, for example, if you add H2CrO4, is that anhydrous or hydrated? That's hydrated, okay? If I add that to one of these molecules, I will get, and I'm going to kind of flip my benzene ring around the other way because it doesn't really matter where it is. I will get, the reason I brought this up, because it relates, and I wanted you guys to see this, because these are actually really important in biology, but also just so you could see an elimination that occurs through an aromatic system. So what happens here is your water is going to pull this. These are going to snap in. These are going to come down. These are going to go over. This is going to go up. And that's going to come off. Okay? I'm writing this particular one because a lot of people cannot draw orthoquinones. This is called an orthoquinone. Remember they're frequently red colored? I talked about that in class. Okay? Draw it like that. Do not draw it like this. There's a lot of this that goes on. A lot of this. I may have said this in class, but I just see lots of really weird looking quinones when I read exams. Okay, so that's one way you could do it. So the idea here, again, this is just like what I just did. It's just that it's like a long range elimination. It's like this is tugging, so it's taking the pies, those take those pies, and so forth through the whole system. And again, quinones are important in nature. They're part of oxidative phosphorylation. The other kind of quinone mechanism I gave you in class, and I gave it to you in some detail, was the reaction of a quinone with, a reaction of a quinone with silver oxide. Okay, and I just talked about how the oxygen here, this is, you have to kind of break this down into two of these and O minus 2. It's kind of ridiculous, the O minus 2, but these are normally done in ether. These are in your cards, and you should be writing these mechanisms out over the course of the week. That O minus is going to take the H off. It's probably hooked to the silver, but I'm just going to draw it that way for the moment, just so you can see what's going on. So I get an O minus, right? And I just made OH minus, so I still have base. That's a more reasonable base. And I have 2 silvers. Silver is like the opposite of, it's like the opposite world to lithium or magnesium. Where lithium and magnesium want to lose an electron, silver, as you know, has 2 oxidation states, +1 and 0. It likes to get an electron, okay? So what's going to happen here is this has extra electrons, okay? This is going to grab an electron from that and become silver 0. See, I like you to see a little bit of this metallic oxidation or reduction. So that's going to become a radical. A lot of students in the class don't realize that radicals are neutral. Okay? So this now, and I'm just showing you 2 different ways an oxidation could take place. This is now a radical because it only lost 1 electron. It's neutral because oxygen is in group 6, right? And if you count up the electrons that belong to it here, it owns half of this bond. You know, but this is like what we call bookkeeping. When you have a bond, you give 1 electron to the O and 1 to the C, regardless of what the real electron density is. It's not really accurate, the bookkeeping. Okay, but you would say 1 of those belongs to the O. So this overall has a neutral charge. But they're still reactive, right? And they're reactive because they don't have an octet. That's something to think about. Okay, so what happens? Well, now we've got a silver 0. Okay, and we have a silver +1. It kind of reminds me of when we do the lithium, which we've done so many times, and I'm not reviewing that today. Okay, and I have this base, so what should happen here? Well, what I think happens is that this pulls this H, and this is a real acidic hydrogen because you get resonance stabilization, and these cascade up, okay, to here. And then this electron, it has to lose 1 more electron. This electron is lost to the silver. So what's the outcome of that? A para quinone. Remember, as I showed you in class, these make really good Diels-Alder dienophiles. They're really good Diels-Alder dienophiles. So don't be shocked in a synthesis problem if one of these is masked as that. You'd have to do the oxidation. Okay, these are on the flashcards. Okay, while I was thinking about it, I think one thing, I'm jumping ahead a little bit, but one thing I think that really, really, really needs to be reviewed is how to make an acyl halide. Making acyl halides is extremely important because you can make pretty much anything from an acyl halide, and I'll demonstrate that in a minute, okay? How do you make acyl halides? Well, the method that I gave you, there's a couple in the sheets, but the main one is to take the carboxylic acid And I'm giving you a little crutch on this, SOCl2. It might just say just SOCl2. Don't be put off by that. I gave you pyridine in class to make your life a little easier in terms of writing this. Okay? People were somewhat disturbed by the fact that I was pulling the proton off with pyridine. This is a carboxylic acid, and carboxylic acids are kind of strong, okay, like compared to an alcohol. You have to get that straight in your head. That's what we started with in the course. Review what you learned about acids and bases. It totally applies in every single thing we do. Okay, so the thing, how does this work? Well, if you put these together, you end up with this. This is also a way to convert an alcohol into a chloride. The reason this is hard to do, and you need these special reagents, is acyl chloride is a terrible nucleophile. It's a really weak nucleophile. So to do any sort of nucleophilic acyl substitution or alkyl substitution, you have to put in a tremendously good leaving group. So this really kind of ties in with what I just did, because I was talking about chromium being a really good leaving group. SO2 is a tremendous leaving group. Okay, so this is the way we trick the chlorine onto the molecule, but once we get it onto the molecule, we can make all sorts of things. Okay, so how does this work again? We just did this a few days ago, but I think it was kind of a little out of sync, so people were a little surprised by it. If you take pyridine, I'm going to use pyridine just to... This is not what you would normally do with pyridine. You usually use the pyridine as a scavenger later in the process because you're not usually dealing with a carboxylic acid. I can't reiterate enough that it's a carboxylic acid. It has a pK of 4. In organic chemistry, that's one of your stronger acids. In Gen Chem, that's like your weakest acid. In organic chemistry, it's one of our stronger ones because we consider alkanes to be acids. And if you didn't get that stuff about acids, I'd go back and look at it again because I think that some people are not on board that this is a pretty good place for charge to be, okay? There were a lot of questions about that. I don't care when you take the proton off. I'm just saying this makes it a lot easier. All right, so then you've got this thionyl chloride, and this is why drawing Lewis structures is extremely important. Some people can't draw Lewis structures, and that's like affecting your ability to do your work. So this is going to go in. All right, and you treat this just like a carbonyl. This kind of reviews flip chemistry. This will come down. I want you to go over this a couple times. Go over every mechanism 5 to 10 times. If you do this, you will probably do well. If you do it in a thoughtful way, if you do it in an unthoughtful way, you probably won't succeed. But if you're thinking about this, you will start seeing patterns. And when you see these patterns, you will not feel like you're memorizing anymore. All right, so this goes in. So look what I did. I kicked out a chloride, so I made the chloride nucleophile. This thing is actually a tremendous leaving group. Now in class, I did this very stepwise. Okay, in class I said this comes down, this comes off, all right? Upon doing that, I have made my acyl halide, okay? I have made this, but this is not the end point, okay? What happens is this, which has a gas encapsulated in its structure, SO2 gas, this is the one I told you is so noxious. The SO2, it's like CO2, it blows off. So it's that idea, again, of Le Chatelier's principle. If one molecule makes it to that point, they all will, because this is a leaving group that's literally leaving. And what do we need? The acyl halide. Why is the acyl halide so important? Okay. It's not the only way, but it is a way to make lots of different molecules. So for example, just to give you an example, like supposing you had to make, I said, okay, you've got to make, I'll do something a little different. So you can see the chemistry I just did. But let's say I say, you got to make this from, let's say I'll give you this just to make life a little more interesting. Because we just did that. Right, if I said you had to make it from that and this alcohol, okay? So say you have those two alcohols, you've got to make that ester. This is not in the right oxidation state. Okay, so first it has to be oxidized. So what the synthesis would entail, and again, one of these days I'll start doing these backwards because you should be thinking of them backwards. Okay? But I would take this, let's say I add, chromic acid. Don't use CrO3 and pyridine. You don't need it. You don't want to make an aldehyde. This is not a situation where I want an aldehyde. I actually want the acid. So what I'm going to add is H2CrO4, and I will make, I don't know if you can see, can you see that? Mm-hmm. A little bit? You would make the carboxylic acid. Now there's lots of ways to make carboxylic acids on aromatics. I showed you a way using Grignards. I've showed you a bunch of ways, but realize they can be made from primary alcohols. And the thing is, you would have to pretty routinely have to turn this into something more activated so that your chemistry would go easily. It's not the only way to do it. There's other ways to do it. I'll show you another way to do it. But if you took that and you made that into the acyl halide, I'll put pyridine here. Then if you add the alcohol to it, right, what's going to happen is this is going to go in, this is going to go up, this is going to go down. By the way, that does not happen all at once. That's going to come off, and then ultimately you would have an ester. But there's lots of ways to make esters, and there's a lot of ways to do that synthesis. Esters can also be made in a very traditional way. You could have taken this, you could take this carboxylic acid. This goes over another part of the sheet, but you could have taken this carboxylic acid and added this to it in the presence of acid. This is what's called the Fischer synthesis. It's a very old-fashioned synthesis. It's an acid-catalyzed synthesis. So you'd protonate here, this would come in here, and you'd spit out water. This is in your notes a couple times. This one should be pretty straightforward for you. I'm not going to do that one in this review. Okay, but you could also make it that way. But generally speaking, there's lots of ways to make esters. Okay, so I could take this and activate it. But the point about the activation, the point about the chloride is that if you've got this species, you really have, and this species is derivable from the acid. All right, if you've got this species and you can derive that from the acid, but that's OCl2, or you can also use like PCl5. There's a couple other reagents, but that's the one I focus on. You can go in a lot of directions. If you add an amine, you make an amide. I want you to think about this. If you add an alcohol, you make an ester. If you add, we don't usually use Grignards on these because they're kind of wickedly bad, but if you use that reagent I just gave you in class, which is this weaker aluminum reagent, I'm going to talk more about that. This is not going to be focused on this exam, but if you use this, you can actually stop it and just make that. Okay, it's a platform. If you add water to it, right, you make the carboxylic acid again. You have to realize that that's your most activated species, and it's something that you can make pretty much anything from with some effort. Okay, now, I want to talk a little bit about protecting groups. What's my time right now?
28 and a half.
Okay, good. I don't know, these might load better as two smaller ones. So I'm going to stop there.
Okay.
So I'm going to stop here. I'm going to continue in a second video just because of the loading issues on YouTube.